Okay, so now for an advanced example of a word problem. And it's advanced even though the word problem is extremely short. Why does the second slope equal minus 1 over the first slope for perpendicular lines? And that's what that symbol means right there, that thing that's basically drawing perpendicular lines. Now, what you're going to need, which we have not gone over, and we do not expect you to know for Math 1011, but you will be expected to learn quickly or know before you even get to Math 1151. The two things that you need are that the cosine law, and that gives you a relationship for any triangle that you can think of, for any general triangle. You'll notice that it might look very similar to something else that you've learned, and we'll get to that in just a second. Now, the other thing is understanding trig functions. Right now we'll work in degrees, though later you'll want to work in radians. But cosine of theta is equal to 0 when theta is equal to 90 degrees. So if I look at this particular equation right here, c squared is a squared plus b squared minus 2ab cos theta. If my cos theta is 0, I'm going to be left with c squared is equal to a squared plus b squared. Now you should recognize that as the Pythagorean theorem for a right angle triangle. And when theta is 90 degrees, that's a right angle triangle. So these are the things that we're going to need to assume that you know before you even get to this advanced problem. Why does m2 equal minus 1 over m1 for perpendicular lines? Okay, well, the hints here, first is that there's two lines. That's the first thing I see there. And that's pretty much, oh, maybe I can also say that they are perpendicular. So the angle equals 90 degrees. So we're going to need an angle in there. And at that special case of 90 degrees, we end up getting this relationship for the slopes. For any other angle, it'll be a different relationship. So maybe what we can do is to to start with two lines at an angle, and then try to say, well, what happens when they get to 90 degrees? So identify. We're going to be identifying our equations or identifying our variables. So we know that we're going to be looking at two lines, so there's going to be some x that we're going to be working with. That's the independent. And in this case, it's just going to be going left to right. So this is our independent variable. We also know that there's going to be two y variables because we have two different lines. So I'm going to say y1 and y2 for two lines. Now if I'm going to draw this, well, I'm going to do this in a little bit more detail in the next slide. Maybe I should switch my colors. Here's one line, and here's another line. Actually, I think I want to rotate this a little bit. Oops, that's not that effective. Here, let's get all of them. There we go. I'm going to want to rotate this for reasons that might become clear a little bit later. So we've got two lines. They're at some angle. I didn't choose it at 90 degrees right yet, partly because it's not so clear on how to approach the problem if you start it at 90 degrees. I'm just going to use the general angle and then see what we get for certain relationships. Now, the relationships that we have, we end up having that y1 is equal to m1 x1 plus b1, and we have y2 is equal to m2 x2 plus b2. And maybe what we'll do, let's say we're going to start right here where they intersect. That's going to be where I set my origin. So maybe I can get rid of my b1 and get rid of my b2. Oops, I meant to select that thing. So this is what I meant when I said, like, after you draw something, that's when I start setting up relationships, because in this case I've defined things so that there's no intercept. They both hit 0. Now, we have to go and do the math before we do any assessing. So let's switch to the next slide. Okay, so starting again, we have two different lines. 1 and 2. Right here. And what I'd like to do, okay, maybe I should be drawing some axes as well. and get them centered on that. That's reasonable. And that is not reasonable. Here we go. Zoom in a bit. Maybe that'll help. There we go. Okay. So what I want to do is I want to choose a particular x. We have two lines, one independent variable, two different positions. So this would be my x right there. And here I have a y1. Oops. So y1. And I also have a y2. Now, with my drawing, it's already starting to get a little bit busy. So maybe what I'm going to want to do is I'm going to want to redraw this. Let's say a little bit down here, so it looks kind of like this. A triangle, and it's not exact, but I mean, I'm mostly trying to shade in or use this triangle right here. And this has a, let's call this A, and this side B, and this side C. And the angle in between those two lines is going to be theta. So that this is reminiscent of the cosine law that we used before, or that I was mentioning before. So c squared is a squared plus b squared minus 2ab cosine theta. Okay, now what else do we need? What else do we know? We know x. Oops. Or we assume that we know x. From x, we know that y1 is equal to m1 times x. And we know that y2 is equal to m2 times x. Now, what do we not know? Well, we don't yet know what A is. And we don't yet know what B is. And we don't yet know what C is to be able to use our cosine law. So let's maybe focus again on one of these particular triangles that we've made up here above and try to find out what one of those sides ends up being. So starting with that y1, and we have x on this side, and this would be A. So this is looking at the triangle that I have down here. And so if I wanted to get A, now because of the way that I've been using x's and y's, those are perpendicular to each other, so that's a right angle triangle. So using the Pythagorean theorem, we know that in this case a squared is equal to x squared plus y1 squared. Now notice that the Pythagorean theorem, you might remember, is something like a squared plus b squared is equal to c squared. Well, in this case, that is relating two of the legs of the triangle to the hypotenuse, where c is the hypotenuse. But in this case, we've already labeled a as our hypotenuse for this triangle, and so we just have to make sure that we've used the correct variables in the correct positions for that relationship. Now, what's useful is that we already have written down that we know what y1 is. We know what it is in terms of x. So here we have a is equal to x squared plus m1 squared x squared. And I'm going to rewrite that as 1 plus m1 squared times x squared. Okay, so we have what a is. We know that a squared is equal to all of that. And so since a squared comes in directly in that cosine law, I'm just going to leave it as a squared instead of trying to determine what a is. So we can repeat this process to find out what b is. So drawing a triangle again for b. Now this is all of this stuff right here. We have that it has a length of x and it has a height of y2. and it has a hypotenuse of b. And so similarly, we're going to get an equation using what we know about y2. We're going to get that b squared is equal to 1 plus m2 squared times x squared. Now the last thing that we don't know is what this c value is. And now if you compare these triangles, our c is like this line right here that's in between y2 and y1. So I'm going to write that c is equal to y2 minus y1. And I can rewrite that as being m2 times x minus m1 times x, which is equal to m2 minus m1 all times x. So if I wanted to find c squared, which is what comes up in our cosine law, c squared is equal to m2 minus m1 all squared multiplied by x squared. Okay, so now we know A, we know B, and we know C, and we have this relationship. And the last thing that we know is that cosine theta is equal to 0 when theta is equal to 90 degrees. So let's set up our equation right here for a squared, b squared, and c squared using when cosine theta is equal to 0. So c squared is equal to a squared plus b squared minus 2ab cosine theta. We know that's going to equal 0 when theta is equal to 90 degrees. So we're left with the Pythagorean theorem, c squared is a squared plus b squared. So putting in our variables from before, m2 minus m1 squared x squared is equal to 1 plus m1 squared times x squared plus 1 plus m2 squared, oops, that squared is inside the parentheses, times x squared. Now in this equation we can divide both sides of the equation by x squared, and so that will eliminate those x squareds, and I'm left with m2 minus m1 all squared is equal to 1 plus m1 squared plus 1 plus m2 squared. Now I'm going to want to expand this out and try to start eliminating terms to see how m1 and m2 are related. So when I do m2 minus m1, it's all squared, then I'm going to have m2 minus m1 multiplied by m2 minus n1. And for the right hand side, I can eliminate the brackets, or the parentheses, so I'll have 1 plus m1 squared plus 1 plus m2 squared. Now on the left hand side, I'm doing first, then outer, then inner, then last. So I get m2 squared minus m2 m1 minus m1 m2, and then plus, or well actually, yeah, I'll just say plus, m1 squared, because I have a negative m1 times a negative m1. And so the two negative signs multiplying together give me a positive. That equals, on the right hand side, I can combine the two ones, 2 plus m1 squared plus m2 squared. And now I can rearrange a little bit. I have on the left m1 squared plus m2 squared minus 2 m1 m2. Remember that it doesn't really matter which way these are ordered, just with regular numbers, and so we can switch them as we need to. And that equals m1 squared plus m2 squared plus 2. Now, I've got m1 squared plus m2 squared on both sides. I can subtract that from both sides, and it gets rid of them. on both sides of the equation. And so I end up with minus 2m1m2 is equal to 2. If I end up dividing both sides by negative 2m1, I get that, maybe I'll use an arrow so that we just rewrite the equation over here. m2 is equal to minus 1 over m1. So here's the relationship between the slopes. This is when theta is equal to 90 degrees for two lines. And so when you have perpendicular lines, you have this relationship right here. Now that was a bit fast, and it's a bit complex, but note that when I was making this, following through the solution, it was really helpful to draw it. If I were to assess my solution, what I could do is say, well, okay, given the way I've assumed things, this is the result that I got. Why don't I test it by drawing? So let's switch over to Desmos, which is an online graphing calculator. There's a number of these that you should have access to through our MyOpenMath website. And I have two lines right here that are set up so that they have that they're starting parallel. You'll see up at the top there's y1, and it has a slope of 2, and I set an intercept of 3. Then the second line, I left the slope as something I can change, as a parameter that I can change, so that I can look at different versions of this line. And so at first, that parameter is 2, and the intercept for that line is negative 2. Now if I were to change the slope of that line using the slider, I'm trying to find when is this going to be perpendicular. So this doesn't look perpendicular yet. It's getting closer and closer and closer. And right here, if I use I've got something here that you can't see, that's at 90 degrees, and that right there looks like a 90-degree angle. So when I start with a slope of 2, and I want to make a perpendicular line, I would get minus 1 over 2, or minus a half. So at least for this example, this solution has worked. Okay, I hope that helps you approach problems, especially this more complicated one,